class called the ins and outs of a steam locomotive. And basically what we're going to try to do is give you some of the things that we have written down on this green sheet here, which is the history, some of the construction. We're going to have a class on the valve gear, boiler construction, boiler feeds, how to operate a miniature engine, troubleshooting, and then the final session is going to be a hands-on operation in which you are actually going to get a chance to operate a miniature steam locomotive. The steam locomotive, as far as our everyday life, is really passed into history. In the 1940s, before World War II, there were almost 50,000 steam locomotives roaming around through the country on various railroads. But today, this machine is so obsolete that it is no longer taught in schools. You can see how fast the technology has advanced. The steam locomotive was a main factor in transportation in this country and other countries of the world for almost 150 years. And it is unfortunate for we lovers of steam that it is no longer used, but it is a fascinating machine to study, and we'll try to make this as interesting as possible. The history of the railroad goes back, well, many hundreds of years, in which it is said and rumored by legend, and even some written knowledge has been put down, where the grooves in rocky streets were made to fit into the wheels of the wagons that passed over them. These grooves had a purpose in which the streets were so narrow that it allowed the wagons to pass. If you were in your groove on your side of the street, you would not collide with a wagon that was moving in the opposite direction. This does make some sense. It is also a known fact that these grooves were cut to an unusual dimension of 4 foot 8.5 inches, which today is standard gauge railroad dimension. In between the rails is 4 foot 8.5 inches. These enterprising, and we'll call them railroaders, soon found that it was better to make rails out of wood and metal, or even just wood, and have the cars fit over the rails. They could pull more. It was easier to make this than it was to cut grooves in the street, and the best part about it is it worked better. Steam, in its early form, was used to pump water from the coal mines in England. It seemed that there was a generally a constant leakage of water into these mines, and it became necessary to pump them out. The early pumps were animal driven, and of course they were limited in their capacity. The early steam pumps that were used were really very crude affairs by today's standards, and alternately used the effects of expanding steam and then cooling it with water. Consequently, they were made very, very large because they were very inefficient. They were made very, very large, and they moved very slowly, as maybe as only 10 or 11 cycles a minute, so to speak. But because they were large, they did pump a lot of water, and it was a great improvement over animal power. James Watt, who was supposed to have discovered the power of steam while watching a tea kettle in his mother's kitchen lift up and down. This makes a good story. Whether it is true or not, history does not really say for sure. But James Watt did contribute a lot to the steam engine. He wasn't the first one who thought of it, but he did improve it a lot. For example, he made the cylinder double acting, in which steam is alternately emitted to one side and then to the other side, and made twice as much power in the same size cylinder. There were other inventors at the time. One was in the name of Richard Trethwick. Trethwick was a pioneer in the use of what they called strong steam or high pressure steam. And the high pressure, I might add, was hardly what we would consider water pressure in some of the apartment houses and buildings. It was just about 50 pounds per square inch. Watt never did approve of this high pressure idea, and consequently his engines, although well made, were probably not as efficient as Trethwick's because of the higher pressure steam used. Trethwick made a motor car in 1802, and he also in 1808 made a little locomotive called Catch Me If You Can. This ran on a small circular track in London and did achieve some attention from some people, and for a shilling you could take a ride on the circular track, but it never really caught on to the great number of people, and particularly those who would have to invest money to build a railroad. There was a Frenchman by the name of Cujo, who was an artillery officer in Napoleon's army. He devised a steam tractor to pull artillery pieces to replace horses. It was very unwieldy, and this was its problem. It was difficult to steer. It moved very slowly, only about 3 to 4 miles an hour, but it did move by itself. In its initial trials, it was wrecked, and Cujo lost interest in this, and so the idea just didn't progress any further. The locomotive, as I mentioned before, Catch Me If You Can, did achieve a speed of about 12 miles an hour, and it weighed almost 8 tons. So it was really one of the very, very first practical engines. On September 27th in 1825, on the Stockton and Darlington Railway, between Stockton and Darlington in England, passenger service was inaugurated. This was the world's first practical steam railway. It was really the birthplace of steam transportation as a commercial enterprise. The engine was called locomotion, of all things. In 1829, the Rainhill trials were held. These trials were to determine what was the best design for an engine, what was the most efficient way they could make it. There were a number of engines entered. There was one called the Rocket, George Stephenson and his son Robert. There was the Novelty, which was by John Harrison, the Swedish inventor, and there was a French entry. They had a number of requirements, one of which no locomotive has ever successfully met, that it must consume its own smoke. The Rocket, George and Robert Stephenson, was the engine that achieved the first prize as being the most practical type of engine. This was in 1829, and by 1829, the locomotive had achieved its outline. Basically, the horizontal boiler, the cylinders in the correct position, the tall stack, the engine had achieved its outline at this time, and for the next 125 to 30 years, it was improvement all the way. In the pioneer in really making small practical steam locomotives as a hobby thing, and of course, as soon as anyone makes anything large, there's always a model maker who wants to make something that looks like it is small. But the idea of a passenger carrying locomotive or passenger moving locomotive was not really approached in a serious manner until The firm of Bassett Lokey made some early in 2.5-inch gauge, but the man who really contributed the most to small steam locomotives was a man by the name of Lillian Lawrence. He wrote in the Model Engineer under the pen name of LBSC. He was born in 1885 and died in 1967. And as a worker, he was a fireman on the London, Brighton, South Coast Railway. He had probably made the greatest contribution of any single person towards the development of miniature passenger moving or passenger carrying live steam locomotives. And this was borne out in the fact that when the Model Engineer conducted a contest, which was known as the Battle of the Boilers, between Bassett Lokey, it was a famous model-making firm in England, and LBSC. LBSC proved that a miniature engine with a small grate with a conventional type locomotive boiler burning coal would be more efficient and run better than a water tube type alcohol burning locomotive that Bassett Lokey contributed. In his lifetime, he designed over 112 locomotives. Actually, he built more than 55 himself. And practically every miniature engine that runs on the rails today has something of him in there, because he was a pioneer in design of feedwater pumps, superheater elements, lubricators, and we owe him a great deal because of the way that he wrote, the way that he did things. And there are other good designers now, many other good designers, but he did it first. So it was with the shame that his passing was, you might say, so soon, but he lived to be over 80 years of age and actually worked up until the last week of his life. The steam locomotive is a simple idea. It's simply you boil water in a confined area and you make steam, and you use the steam to push a piston back and forth, and this turns the wheels. However, in its execution, it becomes somewhat complex. In order to make an engine as efficient as possible, it requires a great deal of work. The steam engine, steam locomotive, and this is primarily what we're interested in, is a heat engine. And of course, we're going to talk about units of heat. A BTU is something you can't see, but it's there. And actually, it's the amount of heat energy that it takes to raise 1 pound of water 1 degree Fahrenheit. Actually, it does take a lot of work energy to do this, because 1 BTU is equal to 778 foot-pounds of work. This means that 1 BTU, in theory anyway, can lift a weight of 778 pounds 1 foot off of the floor. This takes considerable energy. Unfortunately, in locomotives, you cannot use all of this energy that you put into it. So we're going to talk about how much energy it does take to put it in it. The BTU here is a British thermal unit. You can see that. 1 pound of water, 1 degree Fahrenheit. Now, to raise water from 32 degrees to 212 degrees, it takes 180 BTU. And here is where the energy goes into steam. When you raise water from 212 degrees to steam at 212 degrees, it takes 897 BTU. Then, in order to push back the atmosphere, the latent heat that's required to resist the atmospheric pressure is 72 BTU. So when you have steam at 212 degrees pushing back the atmospheric pressure, you have 1,149 BTUs in every pound of steam. It's now a pound of steam, and a pound of steam is the same as a weight as a pound of water, except that the pound of steam occupies a lot more space than does the pound of water. For example, at 100 pounds of steam, water has expanded 1,600 times. So now you have the volume of 1,600 pounds of water, where you only had one before. Steam at 100 pounds has 1,189 BTUs. If you superheat that steam to 200 degrees Fahrenheit, you have 1,250 BTUs. And if you superheated it to 500 degrees Fahrenheit, you'd have 1,430 BTUs. Now remember, each one of those BTUs is the equivalent of 778 foot-pounds of work. So you can see how much energy is crammed into a small space here. Now, miniature engines are notoriously inefficient. By inefficient, I'm talking about their ability to convert the usable BTUs in their coal to, or their fuel, to usable heat energy. In the 1989 model engineer locomotive efficiency trials, the efficiency of the 5-inch gauge engine that won the trials was slightly over 3%, not quite 4%. The efficiency of a 3.5-inch gauge or a 3/4-inch scale engine was less than 1%. But power and torque are related to thermal efficiency, but they are not necessarily dependent upon one another. It is possible to have a highly inefficient engine that will develop a lot of power, in which I'm going to show you right here. Thermal efficiency. The amount of heat we put into the firebox of an engine is 100%. Boilers lose a little bit of this, about 30% to be exact, so that you only have 70% left. And then there's the auxiliaries, the pumps and the whistles and things like that. Take another 8% out of that, so you're down to 62%. Radiation, that's the amount of heat that just is radiated out from the boiler shell, the firebox, it just goes into the atmosphere, is another 3%. Leaks, drips, and steam engines are always leaking and dripping. You lose another 1%, so we're down to 58%. Friction in the mechanical parts, and it does take power to move them, you lose another 4%, so you're down to 50%. But the greatest amount of heat goes from the exhaust steam straight up the stack, 48%. So you end up with only 6% out of that 100% you started with, and this is the power that's used to turn the wheels. Now, you can see that it is a tremendously inefficient machine. However, in spite of this, it is also a very powerful machine. It also has a lot of torque. That's the twisting motion of the wheels. So, in spite of its inefficiency, it ruled the rails for almost 150 years and did a very good job of it. better cut. The second topic we wish to talk about is the construction of this steam machine. We talked a little bit about thermal efficiency and its thermal inefficiencies, but we kind of like to know exactly what goes into the construction of one of these. Now, it isn't my intention to make a finished machinist out of you in this short class. I only want to tell you some of the types of construction you'll probably run into if you observe locomotives, or you may encounter if you're building one. Locomotives are classified, steam locomotives are classified by their wheel arrangement. And by wheel arrangement, the location of their drivers, and if they have a leading truck or a trailing truck, this also enters into the classification. And the classification used is one is known as the White system, W-H-Y-T-E. The types used in this country go from an 040 to a 4884, and we'll talk about some of them in between. The wheel arrangements you see here has two wheels viewed from the side, two drivers as viewed from the side, and a single wheel for a trailing truck. In the White system, you count the wheels on the other side of the engine. So this particular engine would be a 4-4-2. You count the wheels ahead of the driver, you count the wheels, the drivers, and you count the wheels behind the drivers. This would be a 4-4-2, as would be known as an Atlantic type. I'm not going to go into all the types of the locomotives because you can find this in many books, and we don't want to deal with that here. Just some examples is if it had three drivers on the side and a four-wheel leading truck and a two-wheel trailing truck, that would be a 4-6-2 or a Pacific locomotive, just as an example of what it is. The common 040 is just known as an 040 switch engine. It has no particular name to it other than an 040. It is probably the easiest type of locomotive to construct. You encounter different types of frames for locomotives. Generally speaking, engines that are built in Europe or on the British Isles, British engines use what is called a plate frame. A plate frame is just that. It is made out of a plate. It has the notches, we'll call them that, openings cut for the drivers to fit in. This particular one up here happens to be a plate frame for an 040. As you can see, if you turn the plate lengthwise, it is that, just a plate. In miniature engine, this plate could be anywhere from 3/32 to a quarter of an inch thick, depending upon the size of the engine. But it is a plate of steel. All the holes are drilled into this plate. Plate frames are generally easier to make than the American type or the bar frame, which, as you see here, are a section of bars, vertical sections of bars which hold the driving boxes. This type of frame is usually bolted together. However, it could be welded or even silver soldered together. Inside of these openings that you see here, or slots, you have what is known as a driving box, which is a piece that is milled out with a flat section on it to keep it from going through the frame, so it will be able to take outside thrust with the drivers moving back and forth. The driving boxes fit into the slots. They are supported by springs, and they move up and down so that the engine will go over the unequalness in the track. Now, what causes an engine to be able to go over the unequalness in the track is the springing and a system of levers which is known as equalization. The simplest type of engine is perhaps the bar or the plate frame here with the driving boxes in it, and the driving boxes are suspended or supported by springs. The springs cushion the shock and allow each wheel to move up and down individually with the inequalities in the track without bothering the other wheel. Now, equalization is just that. If one driving box goes up through a system of levers and pivot points, it causes the other driving box to go down. If an engine has four wheels on the side, there are more levers of equalization there, but they all do the same thing. If one wheel goes up, it forces the other ones down. If one wheel goes down, it forces the other ones up. Now, with equalization, in order to get the thing that keeps a locomotive stable on the track, it's called cross equalization, in which the leading set of drivers, or with the leading truck up there is a lever that runs from one side to the other with a pivot pin in the center. This is called cross equalization, which provides a three-point suspension. You all know that a three-legged stool will sit on any surface it's placed on. A four-legged stool may not sit on any surface it's placed on because the surface may be uneven. But a three-legged stool will sit regardless of whether the surface is uneven or not. And this is what we have in a locomotive. We have a three-legged stool. This means that the engine has a firm grasp on the rails, regardless of whether the rails are moving up or down, or if they're distorted in any way at all. The equalization allows this machine to roll over the track in order to keep from being derailed. Now that we have some idea of the frame of the engine, let's talk a little bit about size of the engine, because everybody is most interested in the most convenient type of locomotive to operate. The best gauges to have a passenger carrying engine, you can go down as small as 2.5, and we won't go much above 7.5 because most of us are not going to deal with 12 or 15 or higher, larger gauges. The size of the scale and gauge is not as important, but the larger sizes are easier to operate. Everything has its good and bad points. The larger an engine is, the more difficult it is to move, the more expensive it is to build, the larger machinery you have to build the engine, and you have to have more space to store it. Also, when it is necessary to move, it does require more effort on your part. The smaller sizes are easier to move, generally easier to build, less expensive to build, can be built in less time, but they are a little bit more difficult to operate. A good in-between here is if you wish to be 1.5 inches or 7.5, 7.25 inch gauge track, is a 440 or a 260. This is not necessarily a small engine, as even a small 260 at 1.5 inch scale with the tender will weigh over 300 pounds. So as you can see, you do have a sizable piece of equipment to move. A small engine, such as a Titch, an 040 and 3.5 inch gauge, will weigh approximately 22 pounds and will be able to move considerable load on a flat and level track. A Titch has moved as much as 504 pounds on a level track. The grate in a Titch is 2 inches by 2 inches. It has plate-type frame construction. It's a saucy-looking little engine, and it's relatively easy to build. The boiler can be brazed with a gas plate and a couple of propane torches. Size is very important when you're considering which engine you're going to have. But there's one thing to remember, that as far as firing and running, any well-designed engine of at least 15 square inches of grate will give a good performance. When I say a well-designed engine, I mean a matched design. The cylinders, the boiler, the total weight, the boiler output to the cylinders, the water supply to the boilers, the exhaust to keep steam up, to provide the draft to keep the steam up into the firebox and into the boiler. This is all a matched design. Everything depends upon something else. If the work is reasonable, if you do just reasonable amount of work, I'm not talking about super high precision or watchmaking type of work, the engine will run and probably run pretty well. But any break in the chain as far as design is concerned will result in a poor performance. The important part that we'd like to discuss for a moment is this large piece of iron I have in my hand. This is a cylinder casting. It's a cylinder off of a 260. It's a 260 two-wheel leading truck, 6 drivers, no trailing truck, 260 Mogul. It's to little engine's design. I'm told that the cylinder bore is 1 5/8 inches and has about a 3-inch stroke on it. This flat base up here with the 3 slots in it is known as the port face. Those slots are called port openings. This is where the small ones on the outside is where the steam is admitted to the cylinder. The large one in the center is where the steam is exhausted from the cylinder into that large port and up the stack. The most difficult operation is machining these is to get a smooth bore inside. This face must be parallel to the bore. This face must be parallel to the bore. And in achieving this, if you do keep this and this at right angles and parallel to bore and a smooth bore, you will have a good running engine, because this is the way a cylinder should be machined. As you can see, there are a lot of holes in here that have to be drilled and tapped. I'd say before you're done, you have between 40 and 50 tapped holes in each cylinder. Cylinders are really the muscle side of the engine. A well-made cylinder can make a lot of difference in the way your engine runs. This is an important part of the cylinder too. This is known as the valve, the flat D valve. This valve slides back and forth over these portholes like this, alternate admitting steam to one side and then the other side. And when it admits it to one side, it exhausts out of this side through this cavity here and down, out through this hole here and into the stack. This is a D slide valve. Moves back and forth like this alternately while the piston moves back and forth. It is housed in this cavity here, known as a valve chest, which goes on the top of the cylinder in this fashion, bolted down in this fashion with the valve on the inside here. The valve sits inside here and slides back and forth. It is actuated by the valve gear. There are many ways to get cylinders. Usually the way is by casting. They can be built up, they can be soft soldered together, they can be silver soldered together. I have seen some very good cylinders made with soft solder and brass parts with cast iron liners. There is no end to the materials that can be used. In some engines, we have used steel for cylinders because it's obtainable, it's easy to work, and produces a fine finish. The only thing about steel cylinders is that you must soak them good in oil when you put the engine away, otherwise they will rust. Cast iron is probably the best all-around material for cylinders because it's relatively easy to machine, it is very long-wearing, has a high resistance to corrosion, and is relatively cheap. Bronze is also a good one, but it's definitely more expensive than cast iron. We have some new faces here tonight.
You didn't like the ones that were here last night?
Oh, no, I didn't say that. I didn't say that. I said I'm glad to see we had some new ones. I didn't say there was anything wrong with the old ones. We left off, we were talking about suspensions of locomotives, which basically mean how they're suspended above the track and on the track. And we kind of drifted off with a couple of questions and answers, but I think we'd be good to continue with the suspension and give you an idea how leading trucks work on railroad engines and why they put them on. I think we explained the last time that the simplest form of locomotive is one that has four wheels and some springs above the wheels. That's basically the simplest thing you can get on a track. Although they have made some three-wheel vehicles, they were not exactly locomotives, they were self-propelled. This works on good track, but there is another way to do it. Looking at it from the top, in which you have four wheels this way, these are sprung here to go up and down this way, but there's what they call cross equalization here. And looking at it from the front, it's shaped like this. Which there's a spring here, and there's a bar that goes across attaching to the top of the springs, and this weight is suspended in the center of the frame here. That is equalized suspension, which if one wheel goes up, the other wheel goes down. And at the same time, you have springing back here. Now that is about as simple as you can build a locomotive. And of course, as locomotives got bigger and heavier and more powerful, it also got more complicated. Basically, in any engine frame, what you want to achieve is three-point suspension. You all know that a three-legged stool will sit basically at least at some angle, but all three legs will hit the floor. The seat may be tilted a little, but it's going to hit the floor, and it's not going to move. Now, four-legged chair doesn't always sit even because either the floor is out or the chair is out, and you can always have a little bit of a rocking action there. So in a locomotive, what they want to achieve is a three-point suspension. So we'll go back to the wheels again. These are supposed to be wheels. They look like rectangles, but you're looking at them from the top. Now we'll do a look at them from here. Basically, there's a spring here of some sort, either a coil spring or a flat spring. There's an equalization bar again that goes from here to here, springs to there, pivot point here, up to here, and down to springs here. We're back to the same thing. When one wheel goes up, the other wheel goes down. This wheel would go up, it pushes this one down, and pushes this one down. Also, if this one went down, it could lift this one up in the opposite direction. Now, we haven't put a leading truck on here because if you've ever ridden behind an 040, whether it be miniature or full size, you will find as the engine picks up speed, it starts to go this way. This is caused by the piston thrust on the wheels. It gets to saying down the track like this, and a lot of people call this tail wagging, and it's exactly what it looks like. It looks like the engine is going up the track like that, and it is. But this is all right at low speeds, and basically in miniature we do operate at low speeds. But in full-size practice, this can be disastrous. As you can see, the pistons get bigger and the engines get heavier. There's more of this thrust like this all the time. Speeds get heavier, weight gets heavier and speeds get faster, so something had to be done to keep this engine on the track and from tail wagging down it. So somebody devised a lead truck. And they put it out here and just put a couple of wheels and some springs on it. They found out it worked, but it didn't work too good. So they had to devise something else. And so we devised something else too. This is a wooden and metal model of the lead truck. We do have an equalizing bar here someplace. That's a swing link lead truck. When the engine goes around a curve, it pushes in this direction. And notice how that lifts this center pin here? Well, that is on a pivot point here, and that pushes down against these back wheels. It also wants to lift the boiler up because this comes up against the bolster plate on the locomotive. See how those rockers work as you go into a curve? It lifts the front end of the engine up, pushes down on the outside rail, and at the same time pushes down back here so that the lead driver stays on the rail too. Now, the earlier lead trucks were done with simple links, but they found that these are modified. They call them heart-shaped rockers. As you go around a curve, it lifts the front end of the engine up, and the extra weight pushes down against the outside of the curve, because remember, the wheels go into the curve like this, and the engine wants to go straight. So that moves this over like this, raises the front end of the engine, pushes down harder, and keeps the engine on the track. Now this is tied in to the front end by this equalizing bar. Here we go back again to here. So when this goes up, that pushes that down. Keeps the lead driver on the rails, and generally this works pretty good. Most engines stay on the track. Now there's also another type of suspension on the front end, which is known as the four-wheel truck. Has some sort of a springing arrangement. It has two sets of these. Each set of wheels has one of these. Or, as they do, they put two of them in the center, and the pushes on one set of springs in the front and one set of springs in the back, so that the wheels actually operate separately. Now, the four-wheel lead truck is not generally equalized into here. The riding qualities of the four-wheel leading truck are generally good enough that you do not need to tie it into the front end of the driver. However, the Pennsylvania Railroad, that usually did everything different than anybody else, had some locomotives in which the lead truck, four-wheel lead truck, was equalized into the drivers. Now that we've got our suspension built, of sorts, we can proceed on to something to find out how to make this engine go.